Okay, good morning, Professor David J. De Los Reyes. Okay, my topic for this session will be a long video format lecture on alternating current circuit. Okay, let's proceed. My topic for this morning on my alternating current circuit long video format. Okay, this will now be AC circuit lesson number 5. It will now be lesson number 5, and the title of lesson number 5, it will be current calculations under alternating current circuit. Okay, previously we have finished already the discussion on impedance, the total opposition offered to the flow of alternating current. Okay, so we now know how to compute the polar and rectangular equivalent of impedance. So the next topic will be the calculation of current under alternating current circuit. As you can see it later maybe, the computation will be different from the DC circuit. Okay. Let's proceed. The circuit diagram will be something like this. It is just a simplified circuit diagram. For the meantime, we are not even considering a series circuit or a parallel circuit. It is just an impedance connected to an alternating current source. Okay, so the given circuit diagram, it is just the alternating current source, the one coming from the utility line. This is the symbol for alternating. And the connected load is just simply impedance. And for impedance, there are so many variations of impedance. Okay, that's why we discuss first what is impedance, right? There is the so-called pure resistance impedance. There is the so-called inductive impedance, meaning it's a combination maybe of a resistance and an inductance. That's why it is referred to as inductive impedance. And there's the so-called capacitive impedance, meaning a combination of a resistance and a capacitor. That's why it is called the so-called capacitive impedance. Those are the three, but there are some other variations, like if the impedance is a pure XL, that will still be an inductive impedance. If an impedance is just a pure capacitor, okay, that will be a pure capacitive impedance. So actually, there are so many variations of impedance, okay? So also in the calculation of current, there are there are so many, what you call this, form of current that will come out. Okay, it depends on what impedance is connected to the alternating current source. Okay, let's proceed. Case number 1. If we try to compute for the current drawn by an impedance, which is a pure resistance, meaning R plus G0. It's a pure resistance. Okay? How do we compute for the current of a pure resistance, okay, in alternating current circuit? Okay, it's like this. If we try to bring out the voltage of the source in polar form, it is always in polar form. If we are computing current, okay, it's a must that the magnitude you will be using will be the magnitude of the impedance in polar form. Okay? It is not just only the resistance or the reactance, it will be the combination of the two. Okay? So for alternating current source, if we try to bring out the polar form of the voltage, it will be E equal to capital letter E, angle 0 degree. Okay? Under the study of AC circuit, this is the so-called reference vector. We always use the applied voltage as the reference vector. Reference vector meaning, if we try to bring out the vector diagram, it will be a horizontal line. So if we try to bring out the polar form of that voltage, it will be small a equal to the magnitude of that voltage, angle 0 degree. This is voltage E. Okay? It is horizontal, so the angle is actually 0 degree. And if we try to compute for the current, if the load is a pure resistance, okay, it's the same. Voltage is equal to Ij in AC circuit, right? Should be, the applied voltage should be equal to the product of total current times total impedance. Okay, so if we try to compute for I, it will be voltage over Z. Okay, so by using this one, the current drawn by a pure resistance load will be equal to A angle 0 degree. Use the polar form, don't use the rectangular form. It will be R angle 0 degree, okay? And if we try to perform this division here, it will be, the magnitude will be the ratio E over R. And the angle will be, it's like this. It will be the angle of the numerator minus the angle of the denominator. That's the resulting angle. So a 0 minus 0 will be a 0 degree. So in polar form, the current drawn by a pure resistance load will be the ratio E over R, angle 0 degree amperes. Okay, that's the magnitude. That's the magnitude. And if we try to bring out the vector diagram, if you are studying electrical engineering, you should familiarize yourself with this whole vector diagram. So the vector diagram will be something like this. The voltage, applied voltage is horizontal. It is actually E angle 0 degree. Okay? What comes out for the current is also I is 0 degree. Okay? They are both horizontal. And this is the so-called DR in phase. Okay? They synchronize each other. So whatever the angle of the voltage, it will be the angle of the current. That's why if the load is pure resistance, that's the term we are hearing, that the current and voltage are in phase. Okay? And if we try to bring out the graph of this graph here should emanate from the oscilloscope. I got an oscilloscope over here. If you try to bring out the graph of this, the bigger graph is actually the applied voltage, and the smaller sine wave is actually the current. Okay? They are in phase. Okay? The magnitude of the applied voltage, of course, is bigger. It is sinusoidal. And also, the current, what comes out if the load is pure resistance, it's also sinusoidal. Okay? It is this. So, this axis here is time, and this vertical axis represents the voltage or current. For the first graph, it is the voltage. For the second graph, it is the current. Okay? So, on paper, we use the vector diagram to analyze it. And as a technician, if you are in the laboratory, we use the graph. And you can see it as something like this. They are in phase. Okay? O case number 2. If the load is inductive, it's a combination of resistance and inductance. If the load is inductive, it's resistance plus a coil. Right? R and X sub L. The resistance will be R plus Jx sub L. If you try to compute for the current drawn by a combination of like this, okay, compute first for the magnitude of Z. Okay? Do not just divide the voltage by R or by simply X sub L. It should be the value of Z, the triangle portion, right? Do not use this R, do not use this X sub L here or this R here, but use this Z, okay? That's the total, what do you call this, thing that will draw the current. It's the total impedance. It's not only X sub L, it's not only R, it should be the total Z. So if we are given Z equal to a combination of R and X sub L, you should change first the form of the impedance to polar form. Okay, polar form, meaning identify the magnitude, okay, plus the angle, okay, plus the angle. Because actually, if you are given X sub L and you are given R, you could compute for Z, right? And for theta, you could compute for theta also. That was the previous lesson, right? So if we now try to compute for the current drawn by this combination here, it will be the applied voltage E, angle 0 degree. This should be in polar form, okay? Over the magnitude, this hypotenuse. Don't use X sub L, don't use R, use the hypotenuse Z. The magnitude of the impedance, angle theta. And if we try to perform this operation here, polar over polar, right? So the resulting magnitude will be E over the absolute value of Z. That's the resulting magnitude of the current. Okay? The resulting angle should be the angle of the numerator is 0, and the angle of theta, you bring it up, this will not be negative theta. Okay? So for a load that is inductive, meaning for a load that got a coil, the angle is actually negative. Okay, this is negative here. And this is referred to as lagging. If the angle of the current is negative, we term to as lagging current. Meaning to say, if you bring out the graph, if this will be the applied voltage, the current will lag the applied voltage by a certain angle theta. Okay, it depends on the value of X sub L and R. So this negative thing here is referred to as lagging. Okay, that's why I place it here under the vector diagram. This is the applied voltage, and the current lags this applied voltage by an angle theta. This is negative theta. This is the current. Okay, it is below. It lags the applied voltage by a certain angle theta. And if we try to bring out the graph of this using the oscilloscope, the bigger graph will be the applied voltage, and the smaller graph is actually the current. And there is a difference with respect to the origin of these two graphs here. Okay, the start of the applied voltage and the start of the resulting current, there is a gap. And that gap is actually negative theta. That is the so-called angle of lag. Okay? So you now know if the angle of the current is negative, supposed to be the load is inductive. Okay? Okay, case number 3. If we are given a load, a combination of resistance and capacitive reactance, a combination of resistance plus a capacitance, okay? This is R and this is X sub C. In terms of rectangular form, the impedance will be R minus JX sub C. But in terms of polar form, the value of the impedance will be the absolute value of Z, angle minus theta. I place it here, negative angle. Why negative angle? It's a negative angle because this is R and this is X sub C. And this is actually Z, right? And this is minus theta. The angle of the impedance with respect to R is actually negative theta. They are separated by angle negative theta. So if we try to bring out Z in terms of polar form, it will be the absolute value of Z, angle minus theta. Okay? If the impedance has a negative angle, meaning the reactance is actually a capacitance. Okay? And if we try to compute the current in polar form, it will be E angle 0 degree over the absolute value of the impedance, angle minus theta. And if we try to bring out the magnitude of the current drawn by a combination of resistance and capacitance, the magnitude will be the ratio E over the absolute value of Z, and the angle will be 0. We bring this up plus theta. Okay? So the angle of the current drawn by a capacitive load, meaning a combination of resistance and capacitance, it has a positive angle, and this positive angle means leading. The meaning of this, the current leads the applied voltage by certain angle theta. For inductive load, this is minus, that's why it's lagging. For capacitive load, this is plus, that's why it is leading. So if we try to bring out the vector diagram, this is the applied voltage, and the current is actually leads the applied voltage by certain angle theta. This is plus theta, and this is the current. Okay? For the inductive load, the current is downward. It's lagging, right? This is leading. That's why this is leading. Okay? And if we try to bring out the graph of this using the oscilloscope, the bigger graph is actually the applied voltage, and the smaller graph is actually the current. Okay? With respect to the origin of the voltage and the current, there is a certain angle difference, and that angle is actually plus theta. That is actually the angle of lead. Okay? The current was ahead by the applied voltage with respect to the origin by certain plus angle theta. For the lagging, okay, it was behind by minus theta. And this one here, it was advanced by plus theta. Okay, case number 4. Case number 4, if the load is a pure inductive, maybe just a pure motor maybe. The impedance in terms of rectangular form will be no resistance. Okay, it is coil, so there is an exobel. So the impedance in terms of what you call this polar form, the magnitude is just exobel. Okay, there is no R, but there is an exobel. So the magnitude will just be simply exobel. Okay, it is exobel. Angle, what's the angle? It is upward, right? So this is 90 degrees, ohms. And if we try to bring out the current, it will be angle or E angle 0 degree over XL angle 90 degrees. So the resulting magnitude of the current drawn by a pure inductive load will be, the magnitude will be E over XL, right? And the angle will be 0, this 90 here, we bring it up, it will be minus 90. It is minus 90 degrees. Meaning to say, for exobel, for a pure exobel or a pure motor, the current should lag the applied voltage by exactly equal to negative 90 degrees. Okay, it is downward. It lags the applied voltage by exactly 90 degrees because there is no resistance. It's a pure inductive load. And for the graph, it will be this, right? The bigger graph is the applied voltage, and for the small graph will be the current, and the angle of lag is minus 90 degrees. Okay, this is the start of the current, this is the start of the voltage, and there is a difference in angle between angle meaning it is time in real time and using the oscilloscope. The angle of lag is minus 90 degrees. Okay, the last one. For case number 5, if the load is a pure, what you call this, capacitance, yeah, right? The impedance in terms of rectangular form will be 0 minus Jx of z. Because if we try to bring out the graph of this one, it will be just simply downward, right? Minus Jx of z, right? 0 minus Jx of z. There's not even a right triangle. So the magnitude of Z, if the load is just pure capacitance, it will just be simply the magnitude of X of Z, angle minus 90 degrees. Okay, this is minus 90. The first one, it is plus 90 because this is inductive. And if we try to bring out the nature of the current drawn by a pure capacitive load, it will be E angle 0 degree over X of Z angle 90 degrees. The magnitude of the current drawn by a pure capacitive load will be E over X of Z, and the angle should be 0. This is minus 90, we bring it up, so this is plus 90 degrees. So meaning to say, if the load is a pure capacitance load, the load leads the applied voltage by exactly 90 degrees. Okay, this is the applied voltage, so this is the current. and the angle between them is actually 90 degrees. And this is the so-called angle of lead. It is a leading current. And the graph, it's still the same. The bigger graph is the applied voltage. The smaller graph is the current. And the current was ahead by the applied voltage by exactly 90 degrees. So with respect to the reference of the applied voltage and current, there's a gap. And that angle is actually plus 90 degrees. And that 90 degrees is actually the angle of lead. Okay, that's it, guys. That's the 4 variations of current. Okay, how we compute current in alternating current circuit. There are 5 variations: pure resistance load, inductive load, capacitive load, right? A pure inductive load and a pure capacitive load. Okay, so always express the total impedance in terms of polar form. Take the magnitude, you divide that to the applied voltage, that will be the magnitude of the current drawn by that type of impedance. Okay, good morning from Los Angeles. This is Professor David J.